I've just got one slide, which is this one, which I've been looking at for about 10 years. It's well known to most anybody who knows, who's thought about heat and energy and that sort of thing. Now, the bottom line, literally, the electricity demand is there. That's what we're using at the moment. I believe, although I'm not an expert in it, that the system is designed to take some, whoops, let me go back. That. So if we maximize the use of the grid as currently envisaged, as currently engineered, we can probably electrify car charging and the additional bits of housing that comes along which we might make electric. I think that could be done without too much stress on the electricity grid. However, the red bit, which is something that Bob alluded to, is just completely out of the question to do it with anywhere near our electricity grid without substantial changes to it. Now we can talk about, I mean, your supply and demand curve was excellent in what do we do about reducing the demand rather than attack the supply. I've been banging on about demand reduction for a number of years. And I've tried it in my own house. And it's actually quite resilient, the energy consumption of one's house. Resilient. And then you think, well, you know, just throw another couple of $100,000 at it. Surely it will do it. Maybe. And then you think, well, what about a heat pump? What a heat pump would do is occasionally drop if you were achieving that amount of heat using electricity-driven heat pumps, you will exacerbate the peaks because you're not going to get a COP of 3 when it's -10 outside. So you're still going to need the peak electricity demand at some stage. I think the long and the short of it is we need some storage. We need, and I don't think using electricity as a vector will do either. So it would be quite good to combine those two things together into a chemical store, which is kind of similar to gas. In fact, gas is quite a good one. Except natural gas is methane, it's got carbon in it. So why don't you use hydrogen that doesn't have the carbon in it? Now I know there are a lot of problems with hydrogen, which I'm just learning about actually, the fact that it corrodes copper pipes and things like that. But what's encouraging for me is that the government is actually, well, is it pejorative to say for the first time, I believe the government is really taking this seriously now and really looking at, can we decarbonize heat with electricity? Or do we need hydrogen? And there are large-scale tests going on in making hydrogen, seeing whether or not it works. Now, just to follow on, thank you very much for the introduction. The cost of renewables is coming down faster than we think is possible. I've done work in deserts, so I'm quite familiar with those now. They're big, and they get a lot of sun. To manage to generate enough hydrogen to meet these peaks, this amount of energy that we might burn in our homes and also in industry, it's about 577 terawatt hours a year, if you are interested. And to make that, you could generate all that hydrogen from the British Isles using wind The wind output probably follows the electricity demand quite nicely. It's a bit more in the winter than in the summer. If you did it with PVs, you'd have to store more or less all of the energy that you made through the summer. However, if you made it in, say, Namibia, which is big, desert, poor, that's nothing to do with it, but it's cheaper to buy land there than it is in Surrey. The nice thing about that is that, A, it's about half, or to make the hydrogen, according to my figures, it's a half to a third the cost of what it would be in the UK. It also, being on the southern hemisphere, actually matches, I mean, it's not so dramatic as this, but if you're shipping it in using the ships that are currently shipping gas around, actually build a different ship. And the beautiful thing about liquefied hydrogen is that, well, it's quite cool because, literally it's very, very cold. But it's also very light. The density is it's about a fifth that of liquid gas. So these ships they'll be like cruise liners. Most of it will be out of the water. It'd be great. You could even sail them, actually. But the point is that the maximum output from PV in the southern hemisphere would match our heating needs and the shipping across, and so the storage will be reduced. So I think that's, and the other thing is I'd like to reinforce the cost curve. Well, the problem with electrification to making hydrogen is that everyone says, well, it's so expensive to make. Well, it is expensive to make because there is only the number of electrolyzers. Nobody wants it. There's no demand for that. So, it's expensive. The number of electrolyzers is apparently 8 gigawatts in the world, according to Wikipedia. That's a solid bit of research. And I think that to make the amount of gas we needed in, say, Namibia, we'd need 800 gigawatts of electrolyzer. Now, if you say that electrolyzers are quite niche things at the moment, at the beginning of the learning curve, PVs have come down in cost at a rate of about 20% per doubling of capacity. And that's the standard definition of a learning curve. If you apply that to electrolyzer, over a factor of 100, you're going through about 7 halvings or doublings, and the cost of the electrolyzer would be down about 10% of what it is now. All I'm saying is that I think there's reason to be optimistic, but we do need to be given a direction that we are all going to follow, because these problems can be solved, but they need to be done at an industrial level and at scale. And I'm not saying it's going to be cheap, because I'm sure the gas that we get, this hydrogen, is going to be 2 or 3 times the cost of gas that we're paying at the moment. And the benefit of that is that it sharpens one's mind when you open up a gas bill. Instead of it being for, I don't know, 200, 300, 400 pounds, it's actually 1,200. And you might do something about the demand reduction. But at the moment, there's not really much incentive. Anyway, thank you.